A chemistry student through the E-Academy online, and today I will be doing the 07.03 pH lab report of titration. So first we're going to start off with part 1, and I'm going to go over what these are. So this is just a regular beaker, and this is containing the base sodium hydroxide. This is the Erlenmeyer flask, which will be used. This will be where the neutralization of an acid and base take place. This right here is a stopcock. This adjusts how much liquid can go into the Erlenmeyer flask, and this is attached to the burette. This burette will be filled with the NaOH right here, and the burette is just a long, narrow glass tube that the sodium hydroxide goes through into the Erlenmeyer flask. So we're going to start off by putting 50 milliliters into our burette. We'll record that here, 50 milliliters. Next, we're going to take an unknown HCl solution, and we're going to get between 20 and 40 milliliters of that. So we're going to try to stop it right up here. Alright, so we got 25, I'd say, 25.0 milliliters, nice. And now we're going to add 2 drops of our indicator. I'm not really sure how you pronounce that, so I'm not going to try. But this is the indicator is being added into the acid, the HCl solution. So we're going to drop those in, and now we're ready to begin titrating the sodium hydroxide into the hydrochloric acid. And we will know when this reaction is done, the neutralization, because the indicator will turn the solution in the flask a light shade of pink. So we want to go slow. We can go fast for a second, but we gotta go slow, because if you go too fast, you will mess it up. So there we go. So after 12.0 milliliters are added, alright, oops, looks like I didn't stop it. So right here, the reason that you have to go slow is because you're actually, while you're doing this, you're actually stirring the contents. And the reason you're doing that is because you have to continuously be mixing it in. And if you don't, then you will probably end up with too much base in here, and you won't know it because it's going to turn pink once it's neutralized anyways. So if you add a little bit too much, you're not going to know. So you have to continuously stir it. So as soon as you see the color change, you know that it's neutralized. You know to turn the stopcock and not allow any more to go through the burette into the Erlenmeyer flask. So we'll record that, and then we will continue on to our next part. So in the last one, we used an indicator with 2 drops. And this one, we will be using a pH meter, which won't have a color change, but it will be digital, and we can see it. So like part 1, we will be first putting 50 milliliters of NaOH into a burette. And I failed to mention this in the part 1, but it's 25 molar NaOH. So that means there is 0.25 moles in every liter of this solution. So we'll go ahead and get 50 in there, 50. And now we have to get our unknown HCl solution again. So like I just said, the concentration of the NaOH was 0.25 molarity, but this concentration is unknown, and this is essentially the whole point of doing titration, to find the concentration of an acid. So next we're going to turn this on by putting it in here, turn it on, and we're going to record our initial pH of the HCl. So now we're going to record it after, we're going to add 5 milliliters and record the new pH for each 5 milliliters added. So at 10 we're at 1.16, at 15 we're at 1.56, at 20 we're at 7.00 pH. That means it's neutralized now. So we're going to have to record how much we had there. Now we're going to go ahead and keep adding. So at 25 we're at 12.46. At 30 we're at 12.69. At 35 we're at 12.82. At 40 we're at 12.91. At 45, 12.97. And at 50 we're at 13.01 pH. So now we're going to go and look at our data table. So we are not going to do more than one trial. We're just going to do one for the sake of being speedy. And we're going to go ahead and copy this, and we're going to put this into a document. we're gonna put it into our document. So we're gonna put that right here for now, and we can go ahead and delete these two columns because we don't need them anymore. Just like that. Alright, so we're gonna record the observations we made in part 1. So I made a few observations that I pointed out, and the first would be that the two solutions are actually both clear before we began putting them together. Okay, next we're gonna talk about how the solution of HCl turned pink as the NaOH was added. This indicates that it is neutralized. We're going to record what the indicator that we used is. I'm not sure how you say it, and I'm not going to try because I would probably just butcher it, and I'm not really feeling that. And then one more that we're going to talk about is before the indicator actually turned pink, there were little bubbles that formed. Now, this is significant because we actually can balance the equation that we use. So it'll look like this: NaOH plus HCl yields, we'll go ahead and do that, it yields NaCl, which is a salt, plus H2O. So there's a good chance that these little bubbles that I saw are actually just NaCl, salt. Alright, so now we're on to the observations for part 2. So first, the pH. The pH reached 7.0 between the addition of, 7.0 between the addition of 5, 10, 15, between 20 and 25 milliliters of NaOH. Next, we're going to note that HCl is a strong acid with a pH of 0.7. Alright, now we're going to also note that for both parts, the HCl concentration is unknown, while the concentration of NaOH is 0.25 molarity. Alright, now we're ready to make a data table. Now we don't have to make any tables for part 1, but we will need to make one for part 2. And this will be pretty simple, so pull up Excel, and we're going to go from right here, you can see 5 to 50. We're going to put right here 5 all the way through 50 going this way. And when we make this graph, it will actually make the increments 10s instead of 5s because it would take up too much space to do it that way. So now we're going to put the corresponding values. So for 5 it's 0.91 and then 1.16. So 0.91, 1.16. Next we have 1.56 and then 7.0, 1.56, 7.0. Now at 25 we had 12.46. At 30 and 35 we have 12.69, 12.82, so 12.69, 12.82. At 40 we had 12.91, and at 45 we had 12.97. And then at 50 we had 13.01. Now we're going to highlight just the numbers, go to Insert, Scatter Plot is what we want, and we're going to do this. So now we have a graph. So the first thing we want to do before anything else is add a title. So the title is actually composed of the y-axis and the x-axis. So first we'll label this y-axis. This is the dependent variable, which means we do not control it. This is changing based on what we do control, which we control the amount of sodium, the sodium hydroxide is added. So the pH changes with what is with this sodium hydroxide is added. So that makes the x or the y, yeah, the x-axis, the NaOH that is added, and this will be in milliliters. And it's always good to indicate what your values are. And now this will just be the y-axis versus the x-axis. And next we want to go ahead, and I like to add data labels, that way I can see the exact values. And then we want to go to our chart design, add a chart element, and we want to add a line of best fit, like so. And this shows a trend. So when we first start adding our base into the HCl, it slowly increases. And then at this point, it is now pink. It instantly, not instantly, but pretty quickly, it becomes pink. And as you can see, if you add a little bit more than 20, you're not going to really notice that difference. But then as you get to about 25, it goes up here. And as you can see, the same trend from here is going to slowly increase. So it's slow increase, jump, jump, slow increase. So now we're going to copy this graph back into our into our document right here. So the data table has to go there, so I'll go ahead and move that down. The part 1 data table will have to go there too, so right there. Move that down. Okay. So now we're ready to start doing our calculations. So the first thing we need to do, and actually if you go above, so here's this here's our actual lab right here. If you go up, there's a demo that has the instructions, and I will go over how to actually do this. So the first thing we're doing here, and we're going to start doing our calculations. So we have a balanced equation up here. We'll refer back to that. We'll refer to the data table constantly, and we will have to use the knowledge that we have of how reactions occur. So the first question says, for both parts, determine the volume of sodium hydroxide added to the flask from the burette. So both parts we started off with 50 milliliters of sodium hydroxide in each one. So then we're going to be subtracting the amount that is left over. So in part 1, the final reading of NaOH is 12. So that means that there's 12 milliliters remaining in the burette. This means that we used 38 milliliters of NaOH. Now on part 2, it says we had 20 milliliters remaining at the end. So that means that we used 30 milliliters of NaOH. So as you can see, the value comes from right here for part 2. Part 2, 20 and 20. The initial for both was 50, as you can see. And then the final reading for part 1 is 12, which is right there, and 12 right there. So there you have that. Next, we need to calculate the molarity of the hydrochloric acid in the flask. So we can refer back to the titration demo at the beginning of the honors lesson, but instead I'm just going to instruct on how to do that. So the first thing we're going to do for both parts is put our milliliters of NaOH right here. So we're going to move those down, and I'll just copy this one right there. Alright, so they're both going to start off with simple conversions. So in order to find molarity, molarity is moles over liters. So in order to find that, we're going to have to convert this into liters first, of course. So 1 liter, we'll move that over, 1 liter is equal to 1,000 milliliters, and that applies to both parts. So I'll go ahead and copy that down as well. Next, we have to convert from the now this is where the molarity of the NaOH comes in handy. So as you can see from our observations, the concentration of NaOH is 0.25 molarity. As you know, that means that there is 0.25 moles per every 1 liter moles of NaOH. So that is significant because this is going to allow us to convert between the two. So we'll put this down here like that. And now we're ready for the last step. So we've got moles of NaOH now. Now we just need to get moles of HCl. And we can use our balanced equation, and we see that 1 mole of NaOH for every 1 mole of HCl. This equation is balanced without having to add any coefficients, which is also very helpful. So we come right here and we can say 1 mole of HCl for every 1 mole of NaOH. And once again, this applies to both parts 1 and part 2. So the actual finding the answer for this question is actually really simple because the parts are the same except for this initial value. Like the value of the NaOH molarity is the same, the conversions are the same, which is very, very handy. So now we will just multiply this out. So 38 divided by 1,000 multiplied by 0.25, and then that last one will cancel itself out. So right here we have 9.5 times 10 to the negative third, which is also 0.0095. And then and this is moles of HCl. So right here we're gonna follow the same process. 30 divided by 1,000 times 0.25, and we're gonna have 0.0075 moles of HCl. Very, very easy for this question as well. So the question isn't to find the moles though, it's to find the molarity. So if we have the moles, that means we're actually going to be dividing this by another value. And to find that value, we have to find how many milliliters we had of HCl. So the volume of the HCl in the flask is right here, and as we can see, we had 25 milliliters. So we go right here, and we say we had 25 milliliters. And as you might remember, molarity is moles over liters. So this 25 milliliters has to be converted to liters. So we'll go 1 liter for every 1,000 milliliters. And we'll do the same thing here. So we'll go up here to part 2. The volume of the HCl in the flask is 24.2 milliliters. And once again we're gonna have to apply that same conversion from milliliters to liters. Now, this is essentially just acknowledging that molarity equals moles over liters. So as you can see right here, we've got our moles of HCl, and we have our liters. Now this is a kind of complex way to say how many liters you have, but simply put, this is 25 milliliters divided by 1,000. This milliliter right here will cancel with this milliliter when we multiply it out. So we'll go ahead and do that. 0.0095 divided by 25 over 1,000. So there will be some keep flip change involved in this, and we will come up with our molarity, which will be 0.38 m. Now we need to do the same thing for this next one, and once again it's 0.0075 divided by, and as you can see this is divided by this entire thing, so divided by 24.2 over 1,000, so 24.2 over 1,000, and this one will be 0.3 excuse me 0.31 m. So we have our two molarities of HCl for parts 1 and 2 now. So next we're going to go into the conclusion questions. Now the first one says, describe the graph of pH values over the course of the reaction in part 2. Was the change in pH consistent over the course of the reaction? Do your best to explain the reason for the shape of the pH curve in your own words. So essentially it starts off very acidic. So it starts very acidic. And as we add the base, the NaOH undergoes a double replacement reaction with the HCl. So we're going to note that, double replacement reaction. Now, you can see that above in our balance equation. So Na, Na, Cl, Cl, and then H2O. So next we need to note some other things. It does not follow a constant increase. At first, the pH changes very slowly. So you see 0.91, you add some milliliters, you have 1.16, and then now you have a big jump. So this big jump shows that the neutralization takes place pretty quickly. Like adding another 5 milliliters, it's neutralized now, and then you add 5 more, and it's very basic. So it shows that you go from being basic to neutralized pretty quick, and neutralized to basic pretty quick. So it does not follow a constant increase. It is slow at the beginning, then it jumps when it becomes neutralized, and then it jumps again when it becomes basic, and then it has another slow increase period. Okay, so now, why is it important to stir the solution as you add the titrant from the burette? Now, I think I already touched on this a little bit, but essentially stirring is known to increase the rate of reaction. So this ensures that the reaction is completed efficiently and that the base is not added quick enough to skew the results by having too much. If the stirring was not done, then when taking measurements, there would be too much base because we wouldn't have an accurate estimate of when the neutralization actually happened. So if stirring had not taken place, we would have too much base in the solution. So essentially, if you don't stir your solution, no stir equals wrong calculations. Okay, another question. I think that these two questions, numbers 2 and 3, are actually going to answer number 4 for us, but we'll still address it. So number 3, if a student did not remove all the bubbles from inside the burette, what would happen to the calculated concentration of the HCl? So what would happen if the NaOH had a volume that was wrong? So the subtracted amount of NaOH would be higher than what it should be. So essentially this means that the volume would be greater because of the bubbles. So more bubbles equals greater volume. The reason we don't want to have these bubbles is because if the volume consists of pockets of air, it's not consisting of NaOH uniformly throughout. So bubbles mean that the volume is greater, but it's not greater with NaOH, it's greater with air. And that's not good for our results. So this would make the calculated concentration of the HCl higher. So the calculated concentration of the HCl would be higher. And we could show this pretty easily. If there were 2 milliliters of bubbles in the burette and there were 20 of the milliliters were used, then there would be 28 milliliters actually used, but we would record that there were 30 used. If the bubbles were accounted for, the correct calculation would be lower. So right here, I said higher. I was incorrect. The calculated concentration of this would be lower. This is because the initial number that we used right here, 38 milliliters versus 30 milliliters. If we had right here, if we had 50, if there were 2 bubbles of air pockets in here, 2 milliliters of air pockets, it would really be 48 minus 20. And if we had accounted for them, then it would be correct. But if we don't account, then the calculated concentration of the HCl will be lower because the numbers that we are using are lower. Now we wouldn't know that we were wrong because if we knew we were wrong, we wouldn't have done the mistake in the first place. So now we need to describe at least 3 possible sources of error in a titration experiment like this, and for each one, explain whether the error would result in a calculated molarity that's too high or too low. So the first is obviously just recording measurements wrong, or we'll say incorrectly. Now, this could cause the molarity to be either higher or lower because it depends on the mistake you make. Like if you record it as more than what it is or lower than it is, it will change it in one way or the other. Simply put, when you're doing this in a real lab, not a virtual lab, when you're doing this in a real lab, you have to make sure that you are only estimating to significant figures that you know, which is one decimal or one number beyond what you can see. So if it goes to the tens place, you can estimate to the tenths. If it goes to the tenths, you can go to the hundredths, hundredths to the thousandths, thousandths to the 10,000th, and so on. The next possible source of error would be if a variable was not held constant. Now, if the temperature was changing during the reaction, the rate of the reaction would change. So, an example of this example, temperature changed throughout. So if the temperature went up a couple of degrees Celsius, then the amount of NaOH used in the reaction would be lessened. That is because the rate of the reaction would be increased, and we would actually have less NaOH used because it would be neutralizing a lot faster this way. This would cause the molarity of the HCl to be higher than the actual value because the initial calculation involving NaOH would increase. So for example, instead of it being 50 milliliters of NaOH to start and having 20 left, it might be, having used 20, it might be 50 and having only used 15. So this would cause all of the following steps from there to increase. Now a third one, and this is pretty simple, would be messing up the balanced equation. Now this is one that you really don't want to do because, as you can see right here, if you mess up this balanced equation, your answer, where am I at? Right here. If you mess up that balanced equation, you will have an incorrect answer. And once again, this could cause the molarity to go up or down because it depends on how you mess it up. If you increase the molarity if you say that there's this many moles of HCl, more or less, it really could go either way. So if there were more moles of HCl than NaOH in the calculation, which would mean a coefficient greater on the HCl than the NaOH, then the molarity calculation would be higher since the calculated number of moles would be higher. If there are more moles of NaOH, then the calculated molarity of the HCl would be less than what it really is. Okay, so some final thoughts on this lab. So first, for these 2 errors, I think the biggest errors that you could have are actually addressed in number 2 and 3. Having air bubbles in your burette would affect the volume, and that would mean that the entire lab would be incorrect. And if you don't stir the solutions constantly as the dripping is taking place, then you will end up with too much base in your solution, and once again, you will be wrong, but this time you probably won't know that you were wrong. Next, we want to note one more thing, endpoint. I want to clarify that the endpoint means when the solution has reached a pH of 7.0, which means it is neutralized. So aside from that, we will go over this one more time very quickly. So the first thing we did with this reaction was we came up with a balanced equation. We have a base being added to an acid, and we can clearly see that it's neutralized, forming a salt and water. We have our observations for both parts 1 and 2. We have our numbers from part 1 and trial 1 and part 2 and trial 1 for part 2. We have a graph that shows the trend as a base is added to an acid, the pH increases, and if you were adding an acid to a base, the pH would decrease. Next we have our calculations. These are all fairly simple as long as you're paying close attention to what you're actually solving for. So right here, 15 milliliters minus 12, you're just trying to find how many milliliters are left, or how many milliliters were used versus how many milliliters were left in the burette. And lastly, we have our conclusion where we address some of the basic and more complex concepts that take place throughout the titration lab. So this will be the end of my tutorial. Thank you for listening.